This is homework 4, part D. In this video, I will derive an expression for absorption flux of a gas fluxing through a liquid film boundary. So let's draw this. If we can imagine a system where in the middle here is our liquid, and then we have our gas here flowing through this liquid. As it passes our as it flows through our film, which say has a thickness delta, the concentration of our gas will be 0. And so this reaction has a reaction rate K. And it's also a first order reaction, meaning we can model our reaction as we're saying that the rate is equal to our reaction rate K times the concentration of our gas. So since we're looking at our absorption flux here, we can use Fick's law. Which says that our flux J is equal to the negative diffusion coefficient of, say, our gas A throughout our liquid B times our concentration flux, which is just going to be our, looking at how our concentration changes as we move throughout the area, or move along the length. So in our case here, we could say that, so we'll set boundaries. So here we'll say at the interface, position is going to be 0, and then past the film, we'll say that our distance z equals delta. So looking at our flux, molar flux of our gas at the interface where z equals 0, we could say that is equal to the negative diffusion coefficient. So we'll just say d times our concentration flux. It's going to be changing concentration with respect to position. So we also know that we are at steady state, so we can derive an expression for our change in concentration with respect to time, because we know it'll be 0. Excuse me. 0. And that'll help us simplify our expression. So we'll say that our change in concentration of our gas with respect to time is equal to our negative change in flux with respect to position. And the reason it's negative is because flux goes from areas of high concentration to low concentration. So as time progresses, because we're moving from an area of high concentration to an area of low concentration, our concentration will decrease with respect to time because our flux is decreasing with respect to time. And then that'll be multiplied by, we'll add our reaction equation, we'll just say R. Yeah. So we can simplify this. If we plug in our equation for R, so we said our change in concentration with respect to time is equal to the negative change in our molar flux for gas with respect to position plus our constant R, which we said is our rate constant K times our concentration of our gas. So, like we said, we're at steady state, so this is going to be equal to 0. So with that, we could say 0 equals our negative change in flux with respect to position. So we'll also plug in our equation for the molar flux there. We said was our negative diffusion coefficient times, so we can bring that out because it's a constant. We'll take the second derivative of our concentration because we're taking the first derivative of our flux. So we'll say second derivative of our concentration with respect to position. And then we'll add to that our constant K times our concentration. So we'll rearrange this so that we'll solve for our concentration, our second derivative of our concentration. So with that, we could say we'll divide both sides by our diffusion coefficient, and yeah, so we'll say that the second derivative of our concentration of our gas with respect to position, is equal to our constant K times our concentration of the gas divided by our diffusion coefficient. So we can also simplify this further by creating this constant m. And we'll say that m is equal to the square root of our constant K over our diffusion coefficient. So with that, we'll say that the second derivative of our concentration with respect to position is equal to m squared times our concentration. Now, we can apply our differential equation rules to this now. So, rewriting this, we'll say that our concentration is equal to the hyperbolic sign of, concentration is equal to the, hyperbolic sign of our constant m times our position z plus the, this will be concentration is equal to our constant A plus a constant B times our hyperbolic cosine of mz. So to proceed further, we'll need to solve for our boundary conditions. So our boundary conditions are 0 and delta, and so at z equals 0. So this is the solving for the concentration at the interface. So our hyperbolic sign, or just sign, we could say we know it's equal to e to the x, so in this case would be our mz, minus e to the mz divided by 2. And similarly, our hyperbolic cosine is equal to e to the mz plus e to the mz divided by 2. So we can use that simplification in order to help us solve for our boundary condition at the interface. So plugging in, so if we rewrite this equation as our concentration is equal to our constant A times shine, so we'll say e to the mz minus e to the mz divided by 2, and then add to that constant B times e to the mz plus e to the mz divided by 2. So in this case, z equals 0. So e to the 0, we know it's just going to be 1. So this will simplify further down to concentration is equal to A times 1 minus 1 over 2, and then plus our constant B times 1 plus 1 over 2. This will be 0. This will just be 1. So what we'll be left with is our concentration at the interface is equal to B. So that gives us our value for our constant B. Now, our other boundary condition, Z equals delta. If we rewrite our equation so that we say concentration equals our constant A times e to the m delta, or no, we'll actually keep this in just our shine and cosh terms. So say shine of m delta plus B, which we said is the same thing as the concentration at our interface, times cosh of m delta. And rewriting this, we can solve for our constant A. So say A equals our negative concentration at the interface times cosh m delta divided by shine m delta. Okay, so we can now use our boundary conditions to plug into our equation. So because we found our constants, so using our equation for concentration here, we'll say concentration is equal to A, so A being our nice little term here, so negative concentration at the interface times cosh m delta divided by shine m delta multiplied by shine mz and then add to that our other values. So for B, we said B is equal to the concentration at the interface, and then that'll all be multiplied by cosh mz. So we'll simplify this down further. So we could say concentration is equal to, here, let me rewrite this. Concentration is equal to, we'll factor out our concentration at the interface term times our cosh m delta times sine mz plus cosh mz times. So to get this at a common denominator, we'll multiply by a sine m delta, and then that'll all be divided by sine m delta. So we can apply our trig rules now, and we'll say concentration is equal to our concentration at the interface times sine of m minus delta divided by sine m delta. And if we scroll back up to the top, we could plug all of that into our initial equation for our concentration, or for our flux rather. And we'll say that our molar flux is equal to the negative diffusion coefficient of our change in concentration with respect to position. So molar flux of our gas A is equal to our negative diffusion coefficient of our gas A flowing through the liquid B times our change in our concentration with respect to position, because our M and our concentration terms are not changing. We'll just take those out. Say concentration of interface times M times our times cosh m delta divided by sine m delta. And this term is also negative. So these negatives will cancel. And what we'll be left with for our final equation is the flux of our gas is equal to our diffusion coefficient times concentration at our interface times constant m of cosh m delta divided by sine m delta, where we'll say m is equal to the square root of our reaction rate K divided by our diffusion coefficient D. So that'll be our derived equation for the flux of our gas.